Hi there, this is Mladen Jovanovic, and in this video I want to continue talking about injury prediction using Banister model. Maybe you are aware that I already made a video maybe a year ago or a bit more, but I've noticed I made a slight error in that video, so I'm going to try to cover that in this particular installment, as well as cover extra couple of topics, and as well using more metrics than a single metric to predict the injuries. Anyway, I'm going to walk you through the data. So data set is pretty much time series. So the level of analysis is a single day. So each row is a single day. I'm talking about a single individual. So this is one individual. And we have training load per day. In this case, we have RPE load, which is rate of perceived exertion multiplied by duration of the training. We have odometer, which is total distance covered. And then we have high speed distance, which is distance covered over a certain threshold. If I remember correctly, that might be 18 kilometers per hour or more or less. I need to double check, but that's a particular distance covered in a high velocity activity. You can put extra metrics, but for sake of this example, I haven't. If you ask me, the metrics that I would like to go in would be RPE load. It could be odometer and high speed distance, and as well some type of a metric that gives you changes of direction, and particularly that's a 2D player load if you're using a catapult GPS. So not sure how the metric is valid or anything, but the idea behind it gives quite good use to assess the change of direction. So, and start and stop. So you can plug in numerous metrics. The tricky thing might be that the metrics are correlated. So you need to check for that, and I'll cover that a bit later. How to deal with that or how not to deal with that. Most of the metrics will be highly correlated because of the zeros, so you need to get rid of the zeros and then assess the correlation between them. So anyway, as I said, the level of analysis is a single day. If you have multiple sessions on a given day, then you're going to add up the sessions and get a daily load, which is quite easy, just sum up. There is a problem with certain metrics, for example, percentages. If you're using percent of high speed, so percentage of distance covered at high speeds, that's a bit tricky to aggregate on a day. So you might use different. You cannot just put the percentages and then sum them up, because that doesn't make any sense. So I usually don't use any type of percentages. I only use metrics that could be aggregated by summing them up. So we have date, we have injury, which is our target variable, the one we are trying to predict. 0 means there's no injury, and 1 means there's injury. We also have a location, the type of injury. I'm going to scroll it down. So for example, this guy suffered from a hamstring injury, which is a soft tissue injury. Again, there might be different types of injuries, and that's also one of the assumptions of the model. What type of injuries are you trying to predict? So for example, we might build a model to give us the estimate of probability of getting a hamstring injury, and then the model to give us estimate of the quads injury and so forth, rather than just put them all in one same basket and call them probability of getting a soft tissue injury. Why is this? Because maybe some of the metrics, particular physical load metrics, might be more explanatory of certain injuries. For example, hamstring might be more explained by high speed distance or running at high velocities, where groin or quads might be more explained by metrics such as change of direction or start and stop, or accelerating or decelerating. So if we put them all in the same basket, we might get the model that's not really predictive or sensitive. So the only problem with that is we are decreasing the number of instances we are trying to predict. So not many, maybe we might suffer from 1 or 2 hamstring injuries per season, and that's really low number of instances we want to predict. So I guess again, binning all the putting all injuries in same basket rather than trying to predict a particular injury gives us more instances, and there's a pros and cons of both approaches. So because of that, I'm suggesting that the injury prediction models should be done on a whole league or more, rather than only single individual or individual club, sorry, because of the higher number of occurrences. This is something I like to call the injury lead. So how many days we are tagging pre-injury. In this case, I think it's 7, if I remember correctly. So in this way, we are increasing the number of instances, but we also get the warning message earlier. So if I leave this 0 and only leave 1 here, what the model is going to spit out is the probability of getting injured on a given day. But that doesn't give me time to intervene. So we can tag more injuries leading into more days leading into an injury, and then we get the probability of getting injury in this case 7 or less days, and that gives us some time to intervene. Again, what I usually do with some of the models, I try different combinations, so 7, 14, 21, 28, and so forth, and then see what's the most predictive. For example, we might get, if you are using acute to chronic, we might get a big spike. So you might get big spike, and then the injury is actually delayed. It's not going to happen on a big training load spike. It might happen a couple of, maybe 14 days afterward. But we need to sort of align those two for the models to pick it up. So using an injury lead, I believe, gives us more power to pick up those patterns. And if I said something stupid, please correct me. So we have injury lead we can play with. Again, we have injury type we want to predict, or soft tissue, or particular injury location of the injury. And this guy, I think, suffered from 3 or 4. So here he had a contact injury, which is I don't believe it's possible to predict, but it does affect the occurrence of the injuries afterwards. So this, in a way, needs to be taken into account into a model. In this case, it's not. So this is assumption of the model that this doesn't affect anything down the road, and then probably we might put some special feature or interaction that tells us that this guy actually suffered injury in the last contact injury in the last 14, 28 days or 1 month or 6 months. Again, this is again a tuning parameter we might play with. In this case, this is considered non-important. So again, assumption of the model. I think there are 2 more injuries. Yeah. So this is a second hamstring injury. Again, maybe we don't pick that up from the GPS or RPE load if you don't take this into account. Again, it might be a kick in the hamstring or a butt or a low back, and that might cause the injury on the hamstring, soft tissue injury on the hamstring later down the road. But again, the model is not picking that up because it's not taken into account. Again, as I said, we can make different models and then play with that and see what's the most important. So just chugging in the training load might not be the best solution, but might give us some baseline model that we can use and compare different models with different interactions. So yeah, this guy had a couple of injuries. We have a stress groin overuse. Again, it depends how you classify the injuries and things like that. So as I said, we already juggling with 2 things. It's an injury lead and the type of injury. And then we have, as I said, GPS loads. And for the sake of this particular algorithm, I had to normalize the scores. Usually the normalizations, in this case, we need to put all 3 metrics on the same scale, and we usually use a z-score or standard score, but in that case, that goes from pretty much -3 to +3. But for the Banister model, we need to be positive because we already have a positive and negative training effect. And that's why I decided to use standardization from 0 to 1. So yeah, that's pretty much it when it comes to training load metrics. So I standardize it from 0 to 1, and 0 is minimal value and 1 is the maximal value in particular metric. This also makes finding the optimal parameters a bit easier for the optimizer or the algorithm that's trying to find the best combinations. So putting them on a same scale makes it a bit easier to converge, sort of. So when it comes to predicting injuries, so the Banister model gives us 2 components for every training load metric. In this case, we're going to have 6 because we have 3 training loads. So we have a positive training effect, which gives us pretty much the protection from the injury. And then we have a negative training effect that decrease the potential of the injury, probability of the injury. Because injury is 1 and no injury is 0, when we sum all these probabilities, we need to deduct positive training load from the negative training load. So if the protective training load is higher, that means we are approaching 0. So that needs to be deducted. So I'm deducting positive from the negative. That's a slight difference from a usual Banister model. So we have, and as always, I've used the Philips Skiba workbook to get these estimates, actually to implement the Banister load. So we have 3 components, actually 6, RPE Load, Odometer, and high-speed distance. And then we sum them up in a linear combination, which is pretty much what I said. So it's a negative minus positive for each metric. And then we put the intercept, which is so we can start from something that's not 0, and that's also a parameter we want to estimate as well. The error I did in a previous video was the link function I haven't applied after a linear combination, so I applied it in each, I believe, in each training effect. So what I have done was to put the linear combination at the end and then apply the link function. With the link function, we are constraining the estimate of the probability of getting injured to 0 and 1. So it's using exponents and things like that. And you can find that in any statistical book. So it's pretty much sigmoid function that anything, if something is around 0, let me find so it's around probability 0.5. Everything minus 4 is 1, if I remember correctly, and everything plus 4 is everything minus over minus 4 is 0 after the link function, and everything over 4 is 1 after the link function. So pretty much you want to constrain the probability of getting injured to 0 and 1, which is quite logical. But to do that, we need to apply the link function. And usually using this type of logistic function, we usually use maximum likelihood estimation. But I got the error in the Excel. I don't know why. Maybe I'm just stupid or something. So in this case, I use the least square error. So error is just what really happened. In this case, the target variable minus the estimated probability, and then we square that. And the model fit is pretty much summing up of all of the errors. And what we want to do is to try and find the parameters of the Banister model that minimize the error. And for that case, I'm gonna use, where is it? I'm gonna use the solver in the Excel. In the case you don't see solver here, you need to go to a file, and if I believe, go to options and add-ins, and then it should be analysis toolpack, and just click go and enable it. So that's how you use solver. Let me quickly show you the parameters. So these are the parameters for a Banister model. For including the intercept, we have 4 parameters for every training load metric. And this is a sum of the errors I mentioned before. We want to find the best potential solution, a potential combination of these parameters that minimize the error. So in this case, I'm only using high-speed distance, and as you're going to see, the blue bars are odometer, the red ones is the injury and the days when the injury happened, and the black line is a probability of getting injured in 7 or less days. And in this case, I'm only using high-speed distance, so if I change this to 2, you'll see this changing. So maybe 30. So I'm changing the days in the Banister model, the K1 and tau 1 and tau 2. So if I do this manually, it's going to take forever. So that's why I'm going to use a solver. If anyone of you watching knows how to solve this mathematically using an elegant, maybe matrix algebra or something like that, this can speed things up, because the solver might take a couple of hours to find the optimal solution, and the optimal solution might actually overfit, which I'm going to explain a bit later. So if I click on the solver, so data and solver, I want to minimize this cell by changing these variables. And then I need to put some of the constraints, as I said, for the algorithm to make it easy to find the solution, and maybe putting the tau 1 and tau 2 to be integers, so only the whole numbers, and over 1. So I can constrain the number of days. For example, it needs to be over 1 and needs to be below 100, because if it's 0, we get the divide by 0 error. So same for other parameters. So usually in a Banister model, K1 needs to be lower than K2, and then tau 1 needs to be longer than tau 2. So that you can put those constraints here. And then if I click solve, it might take some time, but I already saved some of the solutions. I'm going to click solve and see how it goes. So this might take a couple of minutes or maybe a couple of hours, depends. I'm probably going to stop it and apply the solution that I already saved. So that's one of the problems with the Banister. It's going to take a lot of time to find the optimal solution if you don't create the solution analytically using elegant mathematics. So this might take a bit of time, so I'm going to stop it. So I'm just going to stop. And then I'm going to apply the solution I got here. You can actually play with it and then let it run for a couple of hours and see how it goes. So this is the best solution that I've got after running for a couple of hours. As you can see, this injury could not be picked up pretty much, and these 2 can actually be picked up. So one of the ways to estimate this classification problem is to use a receiver operator characteristic, or ROC curve, which is a bit pain in the ass, to be honest, to implement in the Excel. And that gives us a performance of the model, how good the model is distinguishing between injured or non-injured. So, but in this case, I'm only using a visual, I would say, analysis of this curve. So anyway, as I said, this injury could not be picked up, and these could probably be picked up. Not perfectly, but maybe it gives us some warning here or even here. So that's pretty much it when it comes to this model. I'm gonna cover some other things. So first of all, I mentioned the correlation between the variables. Usually that's a problem when it comes to linear regression, but in this case I don't know how that behaves in a Banister model. So for example, if we have 2 variables that are highly correlated, for example odometer and a training load, they usually tend to be really correlated. That means these factors, so even if we standardize them and then we want to see what what training load metric is the most important when it comes to analyzing the injury or predicting the injury. If the metrics are correlated, then we cannot trust these estimates. But the prediction is going to be still going to be good. So that's pretty much the same as with linear regression. So we might actually use a PCA or principal components and things like that, or remove the variables that are correlated. Again, depends what we want to do. If you want to be really precise, and we don't care what metric is more important or not, then we can leave them. But if you also care about what is the most predictive training load metric, then we might need to deal with correlations. One way to do it is to remove the correlations that are higher than 0.8 or something like that. So again, that's assumptions on the model. And as you already noticed, I already put a lot of assumptions in this model, so we need to pretty much play and see what's the most predictive. And there's a catch-22, of course. This is similar to p-hacking, and to make sure we are not hacking the system and making the model overfit, we need to use cross-validation, or we need to make sure that we estimate the model on a holdout dataset or something that the model haven't seen. And one way to do that is to, we build a model, give it the training data, then we find the best model on the training data. Again, we can use certain techniques such as cross-validation and things like that. I'm pretty much, to be honest, I'm not sure how to do it with the Banister model or time series. But then we say, okay, from this point on, I'm not going to use this data to build the model. I'm going to test how the model predicts on the unseen data, and then we see if the model is predictive of the injury or not. And as you might have read or watched some of my videos, I already warned, because again, correct me if I'm wrong, most of the research, maybe even all of the research on injury prediction in sports doesn't do that. So they are really good at predicting the injury that already happened, and they don't check if the model is actually predicting the injury that's going to happen. So that's a slight distinction, and we need to take that into account. So all these acute to chronic training models might be good at predicting the injury in the history, but I'm not saying they are not good at predicting the future injury. I'm just saying that we haven't, or the researchers haven't estimated the predictive power of that type of model on the holdout dataset. So that's the only thing I want to see in the journals a bit more. Anyway, the other thing with the overfit, we might get the really jumpy estimates, which is also bad, I guess. So the classification problem, if you have 0 here and then we have a 1 here, that will be a perfect classification. But I believe it's going to overfit in the future. So we want to see less than perfect classification between the classes. So we want to see a bit more smooth curve of the prediction. And then again, we can also put that as a constraint in the model. So we might say we are not allowing bigger than certain threshold standard deviation of the estimate. So then we constrain the model to find something that's pretty much smooth and doesn't jump too high from day to day. As you can see, there are big jumps here and things like that. So we want to smooth out the curve. Again, that depends on the training load that's being done. And if I remember, this is the training camp, and this is a training camp as well. So things like that, we might have a double sessions here, and then the probability of injury might spike out. And again, even when we have this estimate, we need to be smart enough to use some type of heuristics, which I'm going to cover in a next video or videos about how to actually implement this in practice. So are we going to allow higher than higher probability of getting injured, but we assume that that's going to protect us from the future injury? Again, it's something that needs to be discussed as well, and I believe that using some types of heuristics might help in that regard in this uncertain world. So again, as I mentioned before, you can play with this model and put, you can even put your own data, see how it goes, and then try to play with the injury lead, or maybe remove some of the injuries, try to only predict the hamstring injury, and so forth. Let me see what I else have to cover. Yeah, so one of the problems is because we are building a model on a particular individual, is that if that individual doesn't have any injuries in the history, we cannot predict anything. So that, unfortunately, that guy needs to be injured. Probably the solution is to have something like similar to Bayesian hierarchical models. So in the case when we don't have any data set in this case injuries for a given guy, we're gonna use we're gonna learn from other cases, and then we're gonna apply that to that particular individual, even if he doesn't have any injuries in his data set. Again, this gives us something that we can use. And again, I'm pretty much in conundrum between this type of analysis and using heuristics, or pretty much don't trusting these risk assessments and be more Nassim Taleb like in ditching all these types of analysis. So again, it gives us something to work with, but we need to be smart enough to know that that's only a model, and then we still need to use heuristics, but we also need to put some of the data from this model to give us the best course of action. So again, it's not just getting these probabilities. We need to deal with other things that needs to be put into our decision making. And I'm gonna try to cover some of my ideas in the next couple of videos. Yeah, I mentioned predictive evaluation. So we need to have a holdout data set, and then use that to actually evaluate the predictive power of the model. I believe that because of all these, the more features you put in, we're going to get more parameters, and that can make the model really, really jumpy. And actually, really, in machine learning, we have bias and variance, and I believe that the Banister model has the higher than usual variance, and we need to make sure that we constrain that, so we don't get really, really jumpy estimates. Another thing needs to, I mentioned the multi-level solution, so Bayesian hierarchical model, and that's beyond my comprehension how that could be implemented into a Banister model. And then we have missing variable and interaction problem that I mentioned before. So for example, maybe there's a third variable, or in this case fourth variable, that we haven't put in a model that's more explanatory. And as I said, there's an interaction also as well. So for example, if in this case, if we have lost maybe a game, or we have a really, really bad start of the season, then the player is going to feel like shit pretty much. And then the training load that they're already used to be doing, it's going to be really, really stressful on the system, or more stressful on the system. But this model doesn't pick that up. So for example, we might put the wellness questionnaire in the model as well, and then put that as an interaction between the training load metrics. So for example, if your wellness questionnaire is worse than normal, and that we multiply, so we negate that, and then we multiply that with the training load, then the interaction with the two is going to spike up. So it means that on the top of feeling like crap, you are putting a high training load, and that might increase the probability of getting injured. Unfortunately, in this particular example, I haven't put the wellness. One problem with the wellness is that we are collecting it not on a daily basis, but maybe once, twice, maybe even more if you're lucky, per week. So some of the researchers binned the level of analysis to be on a week, because then you have data for wellness, and then you have data for all the particular GPS metrics or training load metrics. But that's one of the solutions. But in that case, you need to wait all week until you get the estimates. And if you look from a practitioner standpoint, that might be too long to intervene. Other option is to actually interpolate between the wellness scores. So for example, if I have wellness here, maybe 40, or depends how we standardize the training, the wellness questionnaire. Again, that's again, assumptions that goes into a model. And as I said, the number of assumptions goes exponentially high. And then we can, try all these different combinations, see what's the most predictive and what's most usable. So again, if I have wellness here and then wellness here and maybe here, I have missing values here. And to use that in a modeling, I need to put something here. And usually you can put the missing values here. Usually I put repeat 40, 40, 44, 44, and so forth. It's not perfect, but gets the job done, and you can plug in the wellness into analysis as well. So let me clear this. So yeah, that's one of the things that needs to be covered using interaction, and I think that's called I forgot the statistical term for that. Same thing for the previous injury. So we might say have this guy. Sorry about my bad English. So have this guy already got hamstring injury before. So that could be extra colon. So if I put the extra colon here, previous injury in six months. So 0 for yes, 1 for 0 for no, 1 for yes, and then I can put that into interaction as well, because we already know that previous injury gives the best prediction of the future injury. Same thing for age and things like that. We can chug all this into a model and then try to get the best estimate, get something that we can actually use in practice, gives us the estimation of the probability of getting injured or specific injury. And then if as I said before, if the metrics are not correlated, then we might try to decrease the number of metrics that go in the system. And as I said, one of the best books to read about prediction is Applied Predictive Modeling by Max Kuchen, and he actually talks about feature elimination. So you eventually want to eliminate the features that are not predictive, and then we reduce the size of the model, so makes it simpler and things like that. So this is a Banister model. The analysis could be done differently on these metrics. For example, to aggregate what happened before, which is important. If we plug this all in a linear regression, it's just retarded, to be honest. Not sure if anyone have done it, but it does make sense because the training load preceding this is important. So that's picked up by a Banister. That's why I'm using Banister. And the other option is to remove these. So you remove these and then we put the aggregates. For example, the rolling 7 days average for a RPE, the rolling 7 day sum for the RPE, the rolling 7 days standard deviation for the RPE, and then 7, 14, 21, 28. We increase the number of features, and then we can plug that in a logistic regression or random forest or whatever. So that's one of the things I've been doing lately. Maybe publish something or whatever. I'm not sure. I haven't found anything, or otherwise you will know because I will be a rich guy. So still plenty to do, and I need to go back to my bat cave pretty much when it comes to analysis. Hopefully the idea you got from this video is that injury prediction is not easy. There's a lot of assumptions going into a model, and then again we can use different models. Depends how you classify the injuries, the injury lead, and how you normalize the scores, what scores goes inside, and yada yada yada. And to make sure that we are not p-hacking, in this case overfitting, we need to estimate the predictive performance of the model, not retrodictive performance, but predictive. So we need to estimate the model based on how it performs on unseen or out of sample data. And unfortunately, that's not being done in the journals. And hopefully someone watching this, we need to press the journals or journal editors and reviewers to demand that type of estimation of the model. One more time, this is Mladen Jovanovic from Complementary Training. Thanks for watching, and see you on the blog.